Greetings, welcome. So I've been diddling around with all this and having a lot of fun. Thought I should get another video out. And this one is entitled Return to Voltage Doubler. However, it also implies that there was a first voltage doubler video, which there was, which I noticed no one has watched. And I probably wouldn't watch it either. I don't think that guy knows what he's talking about. No, it was a good video, but when I looked at it, I realized there was a much simpler way of setting the circuit up. Now, my hope was that using this more simple setup, I would get rid of an issue of loss of capacitance that has plagued me whenever you try to increase voltage using capacitors, but alas, it was not to be. Now, I have also started a series on capacitors, and we haven't got to that part yet, but that'll be in the next video concerning when you have capacitors in series, but I'll just kind of give you the cliff notes right now. If you take a 1 UF capacitor and a 1 UF capacitor and you charge them both, so you've charged 2 UF worth of capacitance, and you put them in series, you don't get 2 UF in series, you don't get 1 UF in series, you get 0.5 UF when you connect two 1 UF capacitors in series. So that's kind of an issue. Now I'll just kind of get the lay of the land a little bit more here, and then we'll start from a naked breadboard and just kind of build some stuff and show you what I'm talking about. But, very long ago, when I first started on this, I, like so many others, stumbled onto this guy. Yeah, and that's, of course, John Bedini. I don't want to lionize him too much, but he was very smart, and he built an awful lot of cool stuff, and was a great experimenter. One of the things he said back when I was still trying to figure out, what is the base of a transistor? What does that do, or whatever? And he said something like, no, it works with batteries. That'll never work with capacitors. And I thought, oh man, this guy's got to be just pulling a fast one. You know what? I at least knew what batteries and capacitors were, and I was like, if it works with batteries, it's got to work with capacitors. What I'll show you today is that there's a really quite interesting difference between capacitors, which store energy electrostatically, and batteries, which store energy electrochemically, especially when you are transforming voltage. So I will just go over this now, and then we'll build it and illustrate the difference that I'm talking about. But if you put, as I just said, and we'll cover this in depth in the capacitor series that I'm currently gradually working on. But if you put, as I said, a 1 UF and a 1 UF capacitor in series, the capacitance goes down to 0.5. And that's because you've doubled the space distance between the plates when you connected it in series. And that's also why that voltage transforms. Well, that's not entirely true. I mean, you've gotten rid of 2 of the plates by connecting them together, and the other 2, you've doubled the space between them. So that's why when you connect a 1 UF and a 1 UF, it's not a 1 UF, it's a half UF, because you got rid of half the plates and you double the space between the other ones. That's what happens with capacitors. Now, if you took, I think those are like 250 milliamp hour 9-volt batteries. So if you take a 250 milliamp 9-volt battery and you put it in series with a second 250 milliamp hour 9-volt battery, what's the capacity of the two batteries in series? Is it 125? If you put 4 of them in series, is it 62.5? No, no, no. It remains 250 milliamp hours. And again, because it's electrolytic, it's not, you're not dealing with plate spacing and getting rid of the plates or things like that. So it's a profound difference in terms of transformation of voltage. Okay, we'll tear everything down here and start from scratch, and I'll illustrate for you what I'm talking about. And hopefully this guy's smiling on us. Keep smiling. You know, I've been looking for like an end thing, you know, and stay healthy or whatever. Maybe I'll use that. Keep smiling. That's a pretty good one. All right, let's get to work. So Bedini really was sort of larger than life. He was the grand poobah of all the free energy stuff, and now I'm doing all this silly experimentation, and I love it. So if you have two capacitors like this and you charge them in parallel, so you charge this one, you charge this one, then you shut it down and you connect here to here, and then you look at the voltage here and here, the voltage is now doubled. But as I said, because of how you connected this, you've destroyed charge. You've destroyed capacitance. And the capacitance is now halved, although the voltage is doubled. So in the first video, I did something along those lines. And in this video, you know, the thought I had was, well, you don't even need that cap. That's why I threw it out. You could just connect this to your power supply and double it that way, and that should get rid of the loss of capacitance. Nuh-uh, it doesn't, and I'll illustrate that for you. But if you use batteries, then you don't have the same loss of capacitance. In that case, it's capacity, and I'll try and demonstrate that as well. So let's start to throw something together here. So here's the first part, and we've got pin 2 going to here. Now, as an aside, one thing I'll say is you don't want to use pins 0 or 1 as output, because I tried that and I kept getting a weird error message and it wouldn't compile. And I'm sure the Arduino cool kids know why that is, but these don't work as output, as far as I can tell. And so you want to start with pin 2 or all the way up to 13. So I'm using pin 2 and it goes out to here, and that one turns this on, and then you see that same trigger. That green is a little annoying. It's cool, but it's annoying. That same trigger goes out with blue line to here, and that's grounded, and that turns on the second opto-isolated relay. So the first opto-isolated relay goes from your positive bus to there, and the second to the negative. So now let's just start on throwing a little code together, and we'll say pin 2 high for a second and then pin 2 low for 2 seconds. And so what that will do will be to charge it up through the bus lines for a second, and then when we put a meter on it, this is a very small cap, so it'll just leak out a little bit through the meter for 2 seconds. We'll see it leaking out, and then it'll charge up again. So after we turn the power supply on and put the meter here and compile this, this is just what we want to see. It charges up to 10, and then we just see it leaking out a little bit, and then charges back up to 10. Now, if I recall, what I did in my first voltage doubler video was I had 2 more switches and a second cap like that, and so I charged both capacitors in parallel and then discharged them in series. And what occurred to me was, well, screw that. I mean, just connect this in series with the power supply, and then you have the same thing, but you've saved yourself a bunch of two switches. And what I had hoped, which it doesn't appear to be the case, is that because you're going with just one cap, you would lose the how do I say it? The loss of capacitance from putting two caps in series would disappear. But oddly enough, that doesn't seem to be the case. Let's now get the voltage doubler to work between the capacitor and the power supply. So we need another switch to make a connection between either the positive here to the negative and then go there, or opposite that. So let's set that up. Okay, so we have this now where this charges, and then a connection goes out to here after it's shut down, after it charges, and then goes to the negative. So the positive is connected to the negative, and then you have the negative and the positive, the power supply. And if we slow this down a little, 1 second, 1 second, 3 seconds there, 1 second, this is what we see. Boom, come on, 20, and that's 10. So it's doubled. Wow, that's great. And again, what I thought would be the case, and I'm still confused about this, we'll look at it more as we go along here, is that since there's only one cap, how are you losing all the capacitance? But it seems like you do. There's one last part to this, is that when that is at 20 volts, we want to shunt that off to a big smoothing cap and store it there to use the big smoothing cap as a power supply, the same way that you would use this as your power supply. And I think, I didn't make any video of this, but I think I needed one more switch when I did that. I'm trying to look at it now whether I need another switch or not. Okay, I apologize. It's getting a little complicated now, but it works. And so we have this going into series with the power supply and going up to double the voltage. And I can't figure out any other way but to put in another switch. But the timing of that switch is the same as this switch. So you see this trigger is going out to here. And when it does, then a connection is made between here. What the hell am I doing? No, I had it right the whole time. So the positive to this switch, to the other end of the switch, to there, goes to the positive. And the negative is connected the whole time. So when this is at 20, it connects to here, and then when it flips back to not being at 20, it's disconnected. The timing is the same as that switch, but you need another switch there. And I'll show you how it works. So now we have the power supply across our smoothing cap, and it's kind of cap rebounding, but once we turn it on every 5 seconds, we should see a bump. And it doesn't look like too much right now, but let's speed it up. So instead of a second, let's go with the millisecond. Come back to you. So we got all those as 1 millisecond. Now we'll turn it on and let's see what happens now. There we go. And so we're at 10.3, we're at 20.26. We can go faster. I'm going to go a little bit faster here. Okay, I've gone to 200 microseconds with the 4 switches. Everything's looking great. Yeah, we'll just have a little bit of spreadsheet fun, and then we'll get to the heart of the matter. So just to have a little fun, we've got a 10 UF cap, which is a 0.01 millifarad cap at 10 volts. So it stores 0.1 millicoulombs of charge. We know from here it takes 200, 400, 600, 800 microseconds for this thing to iterate. And each time it iterates once, there's 200 microseconds where this thing is pumping charge into there. So 800 microseconds, and for seconds that would be 800 divided by 1,000, 1,000,000. Oops. That many seconds. So 1 over that equals 1 divided by that is your cycles per second, 1,250. So amps is equal to coulombs per second, and we know this happens 1,250 times per second, and there's 0.1 millicoulombs that is available. So equals this times this. That sounds about right. So at 10 volts, you could draw off 125 milliamps, or 1.25 watts, before the voltage just started sagging to hell. Now, you could maybe go twice as fast, but whatever. I'm just giving the ballpark there. I mean, this isn't integral. I just wanted to have a little fun with it. Now we get to the integral part. Okay, I was thinking I would do this with an LED, but then I remembered LED doesn't behave at all linear with voltage as opposed to the amp draw. So here we instead have a 1K ohm resistor, and I'm going to put it across the power supply. Boom to boom. Okay, so since it's 1K, that's kind of nice. So we're drawing 5 milliamps at 5 volts. Now, if I take this up to 10 volts, we're drawing 10 milliamps. Let's put it back to 5. 5 volts, 5 milliamps. 10 volts, 10 milliamps. So now let's pull this out of here. Remember, 5 volts, 5 milliamps. And we see that this is at 10 volts when we're at 5 there. So 10 volts, 10 milliamps. And I've just taken this and put it out to here. And as we calculated in the spreadsheet, this shouldn't destroy, that dropped a little bit, 9.2, 18.5 milliamps instead of 10. And really it's, there's a little voltage sag. You see what I'm getting at there? I mean, this is the whole party trick. I'll do it for you one more time, and for me. So here we got this at 5 volts, 5 volts, 5 milliamps. Turn this up to 10. Come on. 10 volts, 10 milliamps. Okay. Now back to 5 volts. There are 10 volts across our voltage doubler that we're going to put a load across the exact same amount. Instead of 10, we're drawing 18.8, and this is even sagged, so we'd be drawing 20. So instead of drawing 10, we're drawing 20. Freaking amazing. I say it's amazing because I can't figure out where this is losing capacitance when it's not connected to another cap. Let me try one more thing, because maybe there's a cap in here. So I'm going to try it with the battery. This battery is nearly dead, so hopefully it's at 8.05, 16.1 there, 8.05. But hopefully we'll get our answer. So 8.05, and we should see approximately an 8 milliamp draw if it doesn't just drop to hell. Yeah, 8. Now, we should see 16 here, not 32. Let's see. I haven't really done this yet. 32, essentially. I mean, it's dropping because it's a larger amp draw and the battery's nearly dead. Wow. So even with just that single cap flipping back and forth between the power source, you still get the loss of capacitance. There's one more thing that's important to show you. Okay, so let's forget about this whole voltage doubler for now. Let me get rid of it. Hopefully these batteries are all right. So this one's at 8.71. Now if we put this in, it should be about 8.71 milliamp draw. So we're putting that in, 8.7. And that's gone down a little. Now, I've just put two of these in series that are floating around 17.6. So if we put the same 1000 ohm resistor in, it'll either be a 17.6 or a 35 milliamp draw. And if it's 35, it's like the cap. If it's 17.6, ooh, look at that. It's entirely different. Just to show that a little bit longer. So there it is. And that is not what happened with the capacitor voltage doubler. So going back to the start of the video, I don't know what the hell he was talking about. When Bedini at one point was saying, oh, you can't use capacitors, you only works with batteries. This is something with batteries in terms of transformation of voltage that is entirely different than how capacitors behave. So surprise, Bedini was right again. All right. For anyone who's made it this far, thanks for coming along, and keep smiling, everyone. I'll talk to you again soon. Bye-bye.